Okay, so what we're going to talk about here today, within the world of fluids, is what is referred to as Bernoulli's equation. Now, what we're really going to be talking about here through all this is a lot of physics, but it's a lot of just work energy. Okay, we're really talking about work energy while moving our hands like this for Bernoulli. So let's go back to the idea of work real quick, right? We know from last year when we talked about mechanics that work is just defined as some force dotted with the displacement of an object. So it's the force acting on an object in the direction that the object is moving. So sometimes we call this like delta x for the displacement. Some people call this d, for a distance that it traveled, but it's really a displacement that it travels. Some people call it L, like whatever, right? It is some displacement an object has traveled through. Okay, that is the idea of a work. A force acts on an object, moves it. That's work. So let's think about this for a second. If you have a pipe, I could push with a force on some amount of water here, right? And since a fluid, as we've stated, is incompressible for the purposes of this class and lecture, that means whatever force I exert here on some substance, that force is being exerted down here to move this substance. Now, that makes sense for something like a hose where it's uniform, but let's take things one step further. Instead of just drawing a symmetrical hose, let's draw a system like this. Where we have two different sized openings. We'll call this A1 and A2. And as measured from the centers, they're at different heights. Let's think about all of the different work that we could do now. We still have the idea that if I exert a force here, we'll call this F1, that force on this area, this increase of pressure, has to be applied everywhere. And a very interesting thing about this is, let's think about, if this tube continued on, like if this kept going up here, all of the extra water that would be up here in this region, that extra water is actually pushing back on the water contained in the tube, right? That's why you have that pressure there. So we have this like F2 coming this way. And what this allows us to state early on is that the first amount of work that we're going to have here is a force multiplied by some change in length. We'll call this delta L. We'll call it delta L1. We'll see why we call this delta L momentarily. And since we know that a force can equal a pressure multiplied by an area, we can call this P1 A1 delta L1. On the flip side of things, up here with the force pushing backwards, we can call that W2, and this is going to be negative F2 delta L2. And the reason why this is negative is, we're just pushing back the opposite way. And what this means is that we could rewrite this as equaling negative, well, a force is a pressure by an area, so we'll call this P2 A2 delta L2. Okay? This is all the work that is done to move the fluid. That is the work that is done to just move the fluid. There are other works that we still must do. We need to move the fluid from some initial height to some final height, which means we need to do more work. We need to do work against gravity. This will be work number 3. We know from last year that potential energy due to a gravitational field was mgh, right? So mass multiplied by the gravitational acceleration here on Earth, multiplied by the difference in heights that you were at. Well, this time, when we do this, we're going to get a few things here. First off, this amount of work, we're going to consider it to be negative. We're going to consider it to be negative because according to our conventions right now, we are acting against gravity. And now if we do this, we know this is going to be mass times gravity, and then the delta H here, or we're going to call it for this scenario delta Y. We're going to call up here, up top, Y2. We're going to call down here Y1. So the change in position, final minus initial, is going to be Y2 minus Y1. That's our delta Y. Okay, so we've got work 1, work 2, and work 3. 2 for moving the fluid, and then 1 from actually lifting our fluid up to a new height. And what we're going to do now is we're going to add all of these works together. We're going to get a really large equation here, so get some distance on your paper. Okay? For our very large equation, what we're going to have is this. We're going to say that our work is equal to, well, it's really going to be work 1 plus work 2 plus work 3. And work 1 we defined as P1, A1, delta L1. And then work 2 we defined as negative. So when we add the negative, it becomes negative, a subtraction. And this is P2, A2, delta L2. And then I'm going to split the gravity term up. I know it's mg delta y, or rather negative mg delta y, but I want each of them to be separate. So when I do this, I'm going to actually get negative mg y2. And then I need to be careful here. That negative is actually distributed. And since it's y2 minus y1, when I take the negative of that negative, I'm actually going to get a positive mg y1. So you want to be a little bit careful there whenever doing this. So these are just all of the works we had from above put into one equation. Now, why would we need something like this? Well, there's one thing about work we haven't talked about yet. And if we think about it, when we learned last year in mechanics, we called it work energy, because when you did work on an object, it gained or changed its kinetic energy. And since we know that the work done on an object is equal to the change in kinetic energy, we can say that this work here is equal to 1/2 times the mass times the final minus the initial velocity, or v2 squared minus v1 squared. And you want to be very, very careful here whenever you're squaring these velocities, because technically the velocities are squared and then they're subtracted. Sometimes students accidentally put the square on the outside, and that's not true. If you did that, then you'd have to expand that polynomial into something weird. Let's just be careful about what we're doing, okay? But since we know that this right here in blue, this 1/2 m delta v squared, is equal to this up here, we can set them equal to each other. So let's write out a really big equation now. Writing out big equations, it's what I do. I'm going to start with energy, and I'm actually going to distribute the 1/2 m to each of these. So 1/2 m. I don't know why I put that parenthesis there. That's weird. V2 squared minus 1/2 m V1 squared. And this is going to equal to the P1A1 delta L1. So P1A1 delta L1 minus, because this is the add of the second work, P2A2 delta L2. And then our two gravitational potential energies. So minus mgy2 plus mgy1. Whew. So now we're getting this really large equation here. But if we think about it, we have the work from moving the object, we have the work from gravity, and we've set that equal to the change in kinetic energy, which is what we want here. Now, let's think about a few interesting things we know about fluids. We know that an area multiplied by some change in length is equal to a volume, which means that this A delta L here and this A delta L here are both going to be volumes. And as a matter of fact, both of those volumes are actually going to be the same. They have to be the same volume because our fluid is incompressible. So these are going to become volumes in a little bit. We also know that with fluids, okay, so we switch those greens to oranges, and we know that the A delta L's are going to be volumes, and since the fluid's incompressible, these volumes will be the same. Now, we also know with fluids, dealing with masses is kind of a pain, because it's like, you know, you have the fluid, you don't really think about it in terms of mass. But what we can think about for the fluids is density. We know that a mass can be thought of as a density divided by some amount of volume. And this is very nice because all of the masses that we start seeing in the problem, m, 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 I don't want to deal with those. So it'd be nice if I could get things to kind of turn into more density related topics, and I could get rid of some of those other pieces. So what we can do is this. We know that the mass for the energies on the left here, we're going to turn these into rho. Here, we're gonna fix these masses. We're going to call them rhos over the V's, right? The density divided by the volume. So 1/2, and then this is, I'm going to kind of do two steps here at the same time, so you might just want to hold up in terms of writing stuff down just yet, because we're like almost there. So we've got rho, and then I see an error right here. Density equals mass over volume, so mass equals rho v. Woof. So we're going to get rho v here times v2 squared minus 1/2 rho v. 1/2 rho v times v1 squared. And this is going to equal to P1v minus P2v, and then here for the mg y2 and y1s, we're going to get minus, that m is going to become rho v g y2, and then plus the quantity rho v g y1. So we have this giant flashing yellow equation now for some reason that I do not understand, and it just all went away. Look at that. Set up. And the really interesting thing we see about this is every single term here has a volume in it. And since we know that the fluid's incompressible and all the volumes are the same, when I divide every single term by the volume wipes. So the volume is actually going to go away in this problem. So what we have now is a long equation that reads 1/2 rho v2 squared minus 1/2 rho v1 squared, where those v's are velocities, they're speeds, and that equals p1 minus p2 minus rho g y2 plus rho g y1. And we are almost done with this equation. What we're going to do now is we've basically got a lot of 1s and 2s, things that happen at the beginning of the system and things that happen at the end of the system. Let's put all the 1s together and all the 2s together in this equation. So all I'm going to do here is I'm going to bring this to the other side, and I'm going to bring the P2 and rho GY2 over as well. So when I do this, I finally get the following. All of the values will be positive with all the 1 values and 2 values being on their own side. And I can write this. P1 plus 1/2 rho V1 squared plus rho GY equals P2 plus 1/2 rho V2 squared plus rho GY2. Another way to write this is to say that this left side here, the P1 plus 1/2 rho V1 squared plus rho GY1. Another way to write this is to say that this is equal to a constant. And why is it a constant? Well, that's because what we've just done here is conserved energy. Whatever we've done in the beginning must be conserved. It must remain constant throughout our entire isolated system, where we have not lost any energy due to any weird turbulent effects or friction. This and these right here, these are Bernoulli's equation. This is critical to fluid dynamics. Gotta love the bells. And it's going to be what we're going to be looking at moving forward in some example problems and in this class. But for right now, this derivation of Bernoulli's equation is finished. Until next time, adios and take it easy.